with this? Okay, now we have a start. Good morning, everybody. Good morning, Latin America. This is the LAFMAT network, the Latin American Network of Matter Condensed Physics and Material Science. Today, we have and the invited speaker is Professor Violetta Andreyachshenko. Professor Violetta Andreyachshenko studied material science at Karaganda State Industrial University in Kazakhstan. She is associate professor at the university. She began her scientific career in 2005, conducting research on aluminum alloys and steel in the field of microalloying and nanostructure. En Spanish, buenos días a todos. Esta es la red LAFMAT, Red Latinoamericana de Física, Materia Condensada y Ciencias Materiales. El día de hoy tenemos a nuestra invitada, es la profesora Violetta Andreyachshenko. Ella estudió Ciencias Materiales en la Universidad de Karaganda State Industrial University en Kazajistán. Es profesora asociada a esa universidad. Empezó su carrera científica en el 2005 investigando aleaciones de aluminio, acero en el campo de las microaleaciones y nanoestructuras. Bueno, va a ser la charla del día de hoy en inglés, debido a que la charla es, la profesora habla en inglés. Okay, Violetta, good morning. The whole Latin America says hello to you. You can open your camera, please. Also share your screen and you can start your talk.
Okay. You see my presentation?
It is uploading. Just a second. Okay, it is good. You are in the slide number 1.
You see this slide?
Yes, it is. Yes.
Okay.
Go ahead.
Hello, everybody. Today I want to present the result of a study of aluminum alloys with intermediate composition. Given by the low weight and favorable combination of properties, aluminum, ferrum, silicon-based intermediate can be applied in the mechanical engineering. Thus, understanding of the occurring phase transformation is still limited due to the absence of fundamental studies of the individual and synergetical effect of impurity alloy elements on the final phase composition. This system is characterized by the formation of a number of ternary compounds and stable phases. The main levels of impurity contents in weight percents in aluminum grades are given in table. The simulation was done in the thermocalc software. Selecting the basic composition of the aluminum ferrum silicium system was done on the basis of a model construction of the phase composition for an alloy with a constant aluminum content 60% and a variable composition of silicon and iron with the condition some ferrum and silicium is 40% being met. For comparison, phase diagram is given for traditional aluminum alloy. It's generally known that phase Hydrogen crystal lattice with low symmetry are difficult to process by plastic deformation, and alloy featuring such phases exhibit particularly low plasticity. On the other hand, materials with highly symmetric crystal lattice, such as the cubic and hexagonal ones, are capable to undergo relatively large plastic deformation and demonstrate fairly good plasticity. Based on these facts, the areas of the diagram characterized by PCC solid solution of aluminum and all the alpha phase with the hexagonal crystal lattice are of interest. For the design characteristic lines, the present phase transformation occur. The beta and theta phase are considered to be harmful phase for aluminum alloys due to their morphology. This phase typically have a nuclear structure leading to degradation of mechanical properties. In some cases, they are represented by block inclusions. However, for alloys that consist mainly of intermetallic compounds, the morphology of such phase changes completely and can be represented by large blocks or duplex macrostructure. The primary phase crystallizing from the liquid is the theta phase, and this phase is maintained up to room temperature. The consequence is a large dendritic morphology of the structure and low ductility. Let's consider high-low effect that change in the phase composition of the intermetallic alloy. Copper is one of the most common elements present in all the group aluminum alloys, and its content is typically very high compared to the other elements. The four-component phase diagram of aluminum, ferrum, silicium, and copper shows that even an insignificant presence of copper in the alloy promotes the formation of the tetragonal omega phase, which is an aluminum 7 copper 2 ferrum intermetallic compound. Copper is also present in the salt form in the liquid and in an insignificant amount in the theta phase. The four-component phase diagram shows that even in insignificant presence of copper in the alloy promote the formation of the tetragonal omega phase. Copper is also present in the salt form in the liquid and in a precise amount in the theta phase. Introduction small amount of copper contributed to decreasing the solid's temperature down to 600, but increasing the copper content contribution to increasing the solidus temperature and in the range from 2% to 5% of copper. The solid temperature is 660. The presence of copper also increases the temperature of the alpha-beta transformation, with the alpha phase ceasing to exist already at 5% of copper, while the beta phase is detected up to 11% of copper. The limited area of the alpha phase is associated with the limited solubility of copper in the solid solutions. The theta phase is capable of dissolving of up to 0.5 mole fraction of copper, which leads to its precipitation as in intermetallical omega phase upon cooling. When magnesium is introduced, magnesium silicate is formed, cubic magnesium to silicium compound, and straggling fast in aluminum alloys. Magnesium additives don't affect the alpha-beta transformation temperature. Magnesium can dissolve only in a liquid. Intermetallical phase do not dissolve magnesium, similarly as magnesium silicate does not dissolve iron or aluminum atoms. In general, as magnesium forms a compound with silicon, the proportion of the theta phase in the alloy increases. When introducing manganese to the aluminum ferrum silicium L, it's capable of replacing the hexagonal alpha phase with the cubic lattice alpha phase. It's known that the effective role of manganese is observed with the manganese content of up to 0.5. However, when introducing manganese at the expense of aluminum, the hexagonal alpha phase ceases to form already at the manganese content of 2.6. Manganese doesn't have any fundamental effect on the alpha-beta temperature and doesn't change the liquidus temperature at all. Chromium, similar to manganese, promotes the transformation of alpha H into alpha cubic, significantly reducing the temperature liquid of the modified phase to 250 degrees. The amount of alpha cubic is proportional to the amount of chromium introduced. Complete displacement of the alpha hexagonal phase with the alpha cubic phase is observed with introducing 1.8% of chromium at the expense of aluminum. Nickel can dissolve in the theta phase, but its main part of bound and the nickel aluminate. An exception feature of nickel is ability to completely suppress the formation of the theta phase for an increased temperature range from the liquid phase to 330 degrees. One moment. Unlike the other elements, cell solubility in the phase components of the alloy is very high. This having a low melting point, the zinc significantly reduces the solidus temperature. Titanium, despite its high melting point, does not change the liquidus and solidus temperature of the system, nor the temperature limits of the alpha phase. Neither change the amount of the alpha phase compared to the phase composition. At the room temperature, titanium silicate is formed with the element ratio 1:1. In general, when titanium contained compounds are formed, the amounts of available aluminum and silicon decrease, which leads to increased beta plus amount. Similar to titanium, introduction vanadium is quantities of up to 1% does not significantly affect the temperature of fast transition of the system, with the difference that vanadium, when introduced in the amount of less than 1%, doesn't form stable compounds with aluminum, but with silicon in the silicium-2 compound that does not undergo transformation during cooling. Vanadium in a dissolved form is present only in the PCC aluminum solid solution, along with silicon and iron is not soluble in the intermetallic phase. Zirconium is typically added to aluminum alloys to provide thermal stability by increasing the recrystallization temperature via formation of the aluminum 3-zirconium compound with the zirconium content of 0.2 to 0.4%. However, in the present study, the aluminum 3-zirconium compound was not detected. This is probably caused by the increasing amount of silicon and iron. When introduction up to 1% of zirconium, two types of silicate are formed: zirconium silicate and zirconium bisilicate. Due to the formation and phase transformation of silicates, additional areas on the diagram are formed, but they don't affect the basis components. Zirconium has zero solubility in intermetallic phases. Aluminum is completely absent in its silicates. However, traces of iron can be observed in both the silicon and in zirconium disilicate. Zirconium does not affect the fast transition temperature or the volume fraction of the alpha phase. Introduction beryllium reduces the liquidus temperature of the alloy by 7 degrees and the solidus temperature by 9 degrees. The temperature of the alpha-beta phase transformation does not change, neither does the volume fraction of the alpha phase. Beryllium, without dissolving in intermetallic phases, is able to dissolve aluminum, iron, and silicon. Beryllium forms structural free precipitates without changing the number of phase components. The total effect of impurities alloy elements on the thermodynamical characteristics of the alloys is summarized in this table. Obviously, the simultaneous presence of all the considered elements when using aluminum scrap is unlikely, especially with regard to the weight fraction of the alloy elements. However, when considering such a hypothetical possibility and conducting phase composition modeling simultaneously with all the considered elements, the results in phase composition show that each element has a predominantly similar effect as when evaluated separately. It is worth noting that with the simultaneous introduction of all the elements, the amount of aluminum in the system reduces significantly to 43%. This introduced conditional at which the presence of the alpha phase is thermodynamically impossible. In addition, its cubic modification found due the effects of chromium in manganese are absent, and the low temperature beta phase is also not found. The obtained data on the interaction of the individual elements included in the experimental theoretical alloy contribute to better understanding of the impact of certain components on the phase composition of real alloys and compounds. The phase interaction features are characteristic of aluminum alloys and can be successfully scaled up to industrial processes. This applies to both individual and synergetical effects of the elements. The possibility of the scaling up is guaranteed by the used approach, analyzed all the effect deployed elements in the maximum amount that can be introduced when using secondary aluminum sources. The verify the presented model, a phase composition diagram of the experimental alloys is constructed. As can be seen from the diagram, the feature of the interaction of alloy atoms with each other and with the base elements of the system are identical to those of alloy, which has already been considered. Figure shows the microstructure of the alloys were completely intermetallical with the theta phase identifier with composition aluminum 60, silicium 30. The theta 2 phase, in which up to 9% of silicon was dissolved, and the beta phase. However, the solid solution of PCC aluminum, a product of phase transition during the alpha-beta transformation, was also present in small quantities. Silicon and iron were not detected in the PCC aluminum. Figure 2 shows element distribution map obtained by same for alloys, where obtained CCC, theta, and beta phases. In addition, inclusion of nickel aluminate were found in the metal structure, which was in good agreement with the result of computer modeling. As expected, no additional intermetallic phases were detected. Here shows the microstructure of the experimental alloy using an optical microscope. A comparative analysis of these two alloys shows that both the alloys were intermetallic. In both cases, the crystal growth direction coincided with the heat sink direction. Despite the large production of heated aluminum in alloys, the coagulated effect of magnesium was clearly visible. It was nothing that manganese additive did not completely suppress the alpha-beta transformation, but their contribution to a more favorable phase morphology, which was especially noticed at the interface boundaries. The amount of silicon presence in alloy, which was insufficient for complete ion binding, contributed to an increase in the PCC proportion. The macrostructure photography show inclusion aluminum 3 nickel and 4-2 alloy, also phase omega, indicated by circle. You can see the mechanical properties of the alloys in the table. Verification carried out using the experimental alloys showed sufficient agreement between the results of the simulation and the experimentally observed microstructure. This increasing the reliability of this study. The results can be used in planning alloy of aluminum alloys that are highly enriched with iron and silicium, as well as for identifying the microstructure of real alloys. Thank you.
Okay, thank you very much, Violetta. Can you open your camera, please? Okay. Now we are going to start with the questions from the panelists today. Okay, let's start with, because this is a Latin American community, we are going to start first with Costa Rica, it's in Central America, with Professor Sergio Paniagua. Any questions, Sergio?
Yes, thank you very much for the talk, Professor Violetta. Can you tell us a little bit about the software that you use to simulate these phase diagrams? How does it work? I'm not familiar, so I'm just curious, and maybe I can learn a little bit about it.
I'm sorry, may you write your question?
Or maybe can you translate the question, please, to Violetta in Russian or Kazakh language? Or maybe, I think that we have students here.
I
Let's
can
check.
translate.
Yeah, please. Simbad, please, in your language.
Спрашивает то, что какое именно приложение или программу вы использовали во время эксперимента, чтобы получить графики.
This is thermocalc software version TCL 8.2 base.
Okay, Sergio, more questions?
I guess I will look it up and find out how it works. But thank you. Yeah, very interesting.
Okay. Thank you, Sergio Paniagua. Violetta, Sergio Paniagua is from the university in Costa Rica, in Central America. Well, let's continue with another member, Professor Augusto Moreira from Brazil. Augusto Moreira, University of Pernambuco in Brazil. Your microphone, Augusto, have any question?
Okay. Everybody is listening me. It's okay. The
Yes,
audio
go
is
ahead.
okay. Yeah, no, only nice presentation, Violetta. Thanks. Very interesting. And I have a curious that these materials can be used for what kind of devices? Can you talk about this thing, please?
Thank you. These materials can be used by design elements for its mechanical properties. For example, for steel properties, and these materials have high hardness because it's possible to use by contacting lattice.
Okay. Thanks. Very nice. Congratulations again.
Okay, thank you very much, Professor Augusto Moreira from University of Pernambuco in Recife, Brazil. Okay, let's move to Peru with Professor Henry Moncada. Can you open your camera, please, Henry?
Hello. Sergio y Augusto really stole my questions, so I don't have any question to ask. Thank you.
Okay, they have already questioned the. Thank you, Henry Moncada. Henry Moncada is from the University of San Marcos in Peru. Well, the professor from Mexico is not asking question, who is Alfredo Tablice. He said that has no question. is similar to Mario Reis from Rio de Janeiro in Brazil. But let's say, I think that we have from Argentina, I think that Gabriela from Argentina, University of Córdoba.
Hello, Violetta. Very interesting phase diagrams. Well, they also made some of the questions. I was interested in the code, but I didn't really get which one was. If it was something like Calpad, I guess there is some Calpad code to use to produce this phase diagram. I never used it, but I heard. And about the applications, also you took my questions. But I wonder, how do you produce the data or where do you get the data? You get from experiments, isn't it? The data to feed the program.
Okay, thank you. For produce this alloy, we used synthesis because very difficult to produce this alloy from traditional methods. And how we work with thermocalc for phase studies these alloys.
Okay, thank you very much, Violetta.
Okay, thank you very much, Professor Gabriela Grat from University of Córdoba in Argentina. Before going to Colombia, we are going to ask maybe the Kazakh team has any question. Professor Yomar Kargin from Astana, Eurasian National University, has any question?
Yes. Have you hear me?
Yes, go ahead.
Okay. Good evening, all. I'm glad to see you and to collaborate with all Latin American scientists via our my friend Luis, Professor Luis de los Santos Valadares. My question to Violetta is, Violetta, tell us, please, explain just shortly, does it mean that this is all data which you received in framework of the grant, which funded by our Ministry of Science and Higher Education? Is it theoretical data or experimental as well? Please explain us. Let me. Is it clear, yeah? Or you need to translate?
Нет, я поняла, что... То есть вы, Жуман Пасилекович, здравствуйте, вы спросили, это грант фундаментальный или экспериментальный, да, исследования были?
Да. У меня вопрос, вы могли бы включить камеру? У вас выключена камера, как я так понял, не видят вас, понимаете?
У меня очень слабая связь, поэтому я ее выключила. Просто мне очень плохо видно и слышно.
Нормально, видно, потому что студенты сидят, мы хотим видеть вас.
Да.
Спасибо.
Okay, thank you, Juman Simbekovich. My research from grant Ministry of Kazakhstan is fundamental study. What we was with this alloy how experimental is practical. In practical research, we was by synthesis, by welding, and we produce any alloys with any different elements, and we have a new category of intermetallic aluminum alloys with high hardness and abrasive conduction with high level of, for example, with steel and with aluminum, traditional aluminum. Because we work with fundamental grant, we work only laboratory experimentals. but for transformation our results to industrial, we may produce these alloys in better масштаб. Thank you.
Thank you. Thank you very much.
Okay, thank you very much, Professor Matargin. Yeah, go ahead.
Okay. Second question to Violetta, to you is next. How you manage the composition of your alloys? Because to manage the stoichiometry of some of these alloys is very difficult. How you manage it?
То есть какой состав этого сплава, да? В итоге.
Как вы контролировали? Как вы контролировали?
Как контролировали? Ага. We control the first composition from röntgenfluorescent analyze how first materials and produced alloy.
Okay, thank you. Thank you. Please, next.
Okay. Thank you very much, Professor Karaganda from the Eurasian National University. Violetta, I have invited some students from Kazakhstan, from the Eurasian National University as well. I will ask them if maybe they have questions. They can ask also in Kazakh or in Russian. Students from the Eurasian National University, you have any question? The students?
Yes, I have questions.
Okay, Sinbad.
Thank you. Dr. Andreyachshenko, it was really informative presentation, and it was really interesting to me because firstly, I didn't really close to the alloys. So my question is about what were the dimensions of your test samples for the compression test, and how many samples were there to get the results? Про размеры.
Еще раз на русском вопрос сам повторите, пожалуйста. Спасибо за вопрос. Только повторите на русском.
Про размеры ваших объектов. Какие размеры были объектов, которые вы тестировали?
Okay, thank you for your question. They made размеры is 100 in length centimeters, and it's ellipse, and high wide is 30 centimeters.
Okay.
30 на 100.
Okay, and I have another type of question also. It's about the heat treatment. Like do you apply any heat treatment to these alloys after casting? Термообработка была ли после?
Yes, it's a very high areas of study of research. We use the heat treatment, any kind heat treatment, but I don't show in this presentation these materials because it's very many information, but we used quenching because we need alpha phase instruction our alloy, and we used aniline, but aniline to need in any temperature.
Thank you for the answer.
Okay, Sinbad, for the question, Sinbad is a student from in Astana. Well, any other student has any question?
Can I ask question?
Okay, your camera, please.
My camera? Okay. So thank you for your presentation. It was so informative. And I interested about, can your results be used for designing a load produced from 100% recycled aluminum with high iron and silicon?
Repeat, please, you ask.
Шуха, переводи сразу.
Результаты,
Я не
которые вы
расслышала
получили,
вопрос.
результаты, которые вы получили, можно ли использовать для проектирования 100% переработанного алюминия с высоким содержанием железа и кремния?
То есть можно ли использовать для переработки сплав с высоким содержанием алюминия и кремния?
Да.
Thank you for your question. Yes, we used alloys with high composition ferrum and silicon because in our alloy we have silicon 10% and ferrum 30%. Because we can use scrap with high composition as ferrum as silicon.
Thank you for your answer.
Okay, thank you very much, Suga. Well, I think there are many questions. Okay, thank you very much. And let's check if there is question from Colombia or there is question from the public. Ximena Velázquez from the University of National University of Colombia. Have any question?
Thank you, Professor Luis. Thank you also, Professor, for your incredible conference. But in the network, we don't have any questions. Only the people say that thank you for this topic. This all about theory. No, in my case, I don't have any questions. Thank you for your talk.
Okay, no question said because it is greetings from Latin America. This talk is streamed for many Latin American countries, from Mexico, Costa Rica, Venezuela, Colombia, Brazil, Argentina, Chile, Peru, Bolivia. Well, thank you very much. You are, Violetta, you are very welcome to collaborate with Latin American researchers. And maybe you want to add any word to say goodbye to the Latin American community.
Okay. Firstly, let me should introduce Violetta Andreyachshenko. She's a former my student. She's young scientist. She was graduated Karaganda Industrial University. Initially she's a physical material science scientist in material science, and for Kazakhstan it's one of the lead sphere in the industry, because in Karaganda area we have biggest metallurgical plant nowadays is called as a Karmet, joint stock company Karmet, former ArcelorMittal Temirtau, former Karaganda metallurgical combine, and is this metallurgical plant manufactured about more than 5 million tons of steel every year, and therefore for this metallurgical plant provided all our Kazakhstan needs in metallurgical products, by metallurgical products. And therefore, for Kazakhstan, for Kazakh scientists to study, to research in metallurgy, in material science, in metals is very crucial and very important. And therefore, this study is one of the following of some of the how on the said at the big topics, big themes by nowadays it's studied and carried out in Karaganda Technical University. Nowadays is called as the Saginov University, one of the famous, one of the biggest Kazakh universities. So, and thank you very much first of all, I'd like to thanks to Professor Lewis for inviting me, for inviting our students to collaborate with, directly collaborate with the scientists from all Latin American countries, as we have had from Brazil, Mexico, Costa Rica, Colombia, Argentina, and so on. So, of course, Peru as well. And thank you very much to Professor Andreyachshenko Violetta, because this topic was very, very interesting. Thank you very much. We wish you just to be continue this work and to receive more important data and finding. And thank you very much to all our students for participated to this seminar, to this video conference, and thank you, and see you once again in future.
Yeah.
Thank you.
Violetta,
Thank you.
any final words, Violetta?
What?
Any final words?
Yes, I want to say thank you for your attention, thank you for your question, and thank you for your voice, and thank you. It's very interesting option for me because it's first my lecture for these auditoriums.
Okay, nice. Thank you very much. Please, the rest of the people, the audience, open your camera and your microphone to say goodbye to Violetta, please. Open your cameras and your microphones to say goodbye to Violetta. The students, open your camera and your microphone to say goodbye to Violetta. Okay. Goodbye. Bye.
Bye.
Bye. Thank you.
Bye.
Bye bye.